Hello everyone, I'm Dr.S.Shanmugasundari, working as an assistant professor at PG and Research Department of Physics, Lakshmi Ramaswamy College, Trichy. Today we are going to see about the modulus counters. Counters are nothing but a versatile digital system, and these counters are driven by the external clock pulse. And we know that the external clock pulse occurs at a particular interval. Thereby, these counters are very useful to count the time period and the frequencies. Mostly these counters are constructed using this flip-flop. We know that we have three flip-flops. One is a JK flip-flop, RS flip-flop and a D flip-flop. So out of these three flip-flops, we are using mainly this JK flip-flop to construct this counters. These counters can start counting from any number. It can be of 0, 1, 2 or at any desired numbers. So the main characteristics of these counters involve, it can count the number of counts in a particular cycle. It can be in asynchronous or in a synchronous mode that we are going to see in the later part of this presentation, or it can be in the ascending mode or in the descending mode, or we can say it can be in count up mode or in the countdown mode. So for an example, now we are going to see how to construct the smart 4 counters. So whenever we are going to design a counter, we should know how many number of states that the counter is going to count up. So that we used to call it as number of states. So in this case of mod 4 counters, it is going to count 4 states. So now let's start making this counter counting from 0. So 4 states means 0, 1, 2 and 3. So next step, we should aware of how many number of flip-flops that we are going to count. So for that, we have to make use of this formula 2 to the power n. So 4, we can write it in terms of mod 4 in the sense we can write it in terms of 2 power 2. So it is nothing but 2 to the power n. So this n symbolizes the number of flip-flops that are required to construct this counters. So here the number of flip-flops required to count this mod 4 flip-flop is nothing but 2. So what will happen when we are constructing the mod 8 counters? 8 means we can write in terms of 2 as 2 to the power 3. So we should use 3 flip-flops to construct this mod 8 counters, and we can make them to count from 0 to 7. So this 7 is called as the maximum number that the flip-flop can count in this case of mod 8 counters, whereas in this case of mod 4 counters, 3 is the maximum number, or we can say 3 is the maximum number or the state that the mod 4 counters can count. So the maximum number that the counter can count is given by the formula called 2 to the power n minus 1. So 2 to the power n is going to give us the number of flip-flop that we are going to use, and 2 to the power n minus 1 is going to let us know what is the maximum number that the counter can count. Next, we need to know how the counter is going to perform, either in the asynchronous mode or in the synchronous mode. That is the first thing we should come out of it. So asynchronous in the sense the first flip-flop is driven by the external clock pulse, whereas the subsequent flip-flops, either it can be of second flip-flop or the third flip-flop, will be driven by the output of the previous flip-flop. See here, in this the first flip-flop alone is driven by the external clock pulse, whereas the second flip-flop is driven by the output of the first flip-flop, and the third flip-flop is driven by the output of the second flip-flop. Whereas in the case of synchronous counters, how many number of flip-flops, whatever we are using, all the flip-flop will be driven by the external clock pulse. As an example, see here we have used in mod 4 counters. The first flip-flop as well as the second flip-flop are driven by the external clock pulse and not by the output of the previous flip-flop. So this is the basic difference between the asynchronous and the synchronous counters. The other name of asynchronous counters is called as a ripple counter. So now we are going to see about up, down and up, down counters. Up counters in the sense it is going to count in the ascending mode. Either it can be from 0 or from the 1. In the incremental order it is going to count. So in the down counter means it is going to count in the descending mode. That is the difference between up counter and the down counters. And we can design up, down counters with the help of some gate circuit where we can choose either it can be in up counter or maybe in the down counter mode, but subsequently they can't count both up and down mode. Either it can be in up mode or can be in the down mode. So that is called as up down counters. So now we are going to see about the designing of Mod 4 counters. So first we should know how many number of flip-flops are required. So for that we know the formula. It is 2 to the power n. So Mod 4 means we can write it as 2 to the power 2. So the flip-flops required is nothing but 2. And how many number of states that it can count is nothing but Mod 4 means 4 counts. So 0, 1, 2, 3. So 2 to the power n is equal to 4. So it can count only 4 states. And the maximum number that it can count is given by the formula 2 power n minus 1. So it is 4 minus 1. So the maximum count the Mod 4 counter can count is nothing but 3. So now we are going to see about the designing of our asynchronous counters. So the asynchronous counters, in the sense we know that the first flip-flop are driven by the clock pulse. The second flip-flop is connected to the output of the first flip-flop through QA. QA is working as a clock for the second flip-flop. And we know this symbol indicates though all the 2 flip-flops are negative edge trigger flip-flop. So now we are going to see how this Mod 4 counter is going to work. So this is the external clock pulse. So whenever there is a transition in the external clock pulse, the first flip-flop, that means our A flip-flop is going to toggle. So initially all the flip-flops are at the set stage. So now there is a negative edge trigger. So there is a toggling. So again for the first clock pulse, second clock pulse, third, and so on it goes, right? So the QA flip-flop is toggling between the states whenever there is a negative edge trigger in the external clock pulse. If the QB flip-flop is independent of the external clock pulse, so it depends on the QA. So here there is a negative edge trigger, and here there is a negative edge trigger, and here also we have a negative edge trigger. So initially the flip-flop is at the set stage, and for this negative edge trigger it is going to reset, and it remains in the reset state till the next negative edge trigger is happening in a QA flip-flop. So here it is going to get toggle, and it remains in the set mode till the 4th clock pulse of the external clock pulse, and again it is going to toggle because there is a negative edge trigger in the Q flip-flop. So it goes on. So this is the corresponding truth table of our Mod 4 counter. We'll see how we are going to do the truth table. Okay, so this is a 0, 1, 0, 1, 0, 1, and here it will be remain in the reset state. Then again it is going to toggle for 0. Then again here also it is going to be 0. Yes. So now we'll write. So for the first flip-flop, see here, this is the first clock pulse. So it is 0, 0. And for the second clock pulse, it is 1, 0. And the third clock pulse, 0 and 1, 0 and 1. And for the 4th clock pulse, it is 1 and 1. And when it comes to the 5th clock pulse, see here 0 and 0. So the corresponding decimal numbers are 0, 1, 2, 3. So for the 5th clock pulse, automatically it is start counting from 0 again. So now we are going to see about the down counting mode. So we know that for the up counters, we have connected the second flip-flop to the Q naught, isn't it? So when we are going for the countdown mode, the only difference between the up and down mode is instead of connecting to the Q naught, we have to connect the second flip-flop to the Q bar. That is the only difference. So when the second flip-flop is controlled by this Q naught bar, automatically it starts counting in the descending mode or in the countdown mode. So now this is the clock pulse diagram. So Q naught, there won't be any change. Instead of following this Q naught, we need to follow the Q naught prime for this countdown mode. So we are just drawing the mirror image of this Q naught. So based on this Q naught, the negative edge triggering, the Q1 is toggling. See here, so 0, 0, 1, 1, 0, 1, 1, 0. So this is the corresponding truth table for the asynchronous countdown mode, Mod 4 counters. So 0, so initially at the 1 stage, and then it is going to the second, then it is going to 1, then it will comes to 0, again it will start at 3. not from 1. So this is the difference between count up and the count down mode. So now we are going to see about the subsequent up down counters. So in this case of up down counters, we need some control circuit. So this gate circuit is called as a control circuit, where we can choose between either the flip-flop can work in the up mode or in the down mode. So if we give 1 for this up mode, automatically the first NAND gate will get enabled and the flip-flop will work in the count up mode. If we give down is equal to 1 and up is equal to 0, then the second flip-flop will get enabled and it will automatically count in the down mode. So the corresponding truth table for count up high and then count down high are given here. Now we are going to see about the designing of mod 8 counters. So it is nothing but it is going to count 8 states. So it means 0, 1, 2, 3, 4, 5, 6 and 7. So how many flip-flops are required to construct this mod 8 counters? And it is given by 2 to the power n. So 2 to the power n means in the case of our mod 8 counters, it is 2 to the power 3. So we need 3 flip-flops. So we have used 3 flip-flops here, and then we need to decide whether it is in the synchronous mode or in the asynchronous mode. So here we are using only the asynchronous counters. So the first clock pulse, first flip-flop alone is driven by the external clock pulse. The subsequent flip-flops are driven by the previous output flip-flops, right? So the second flip-flop, see here, Q is connected to the second flip-flop. This Q is connected to the third flip-flop. So as Q is connected here, it is going to work in the count up mode. If we connected Q bar as a clock, then it will be working in the count down mode. So this is the clock pulse diagram. So based on the negative edge triggering of the clock pulse, the QA is toggling between the states. See, initially all the flip-flops are at the reset stage, and when there is a negative trigger, the A is toggling from reset to set, and then it maintains in the set stage. Again, it will come to the reset when there is a negative edge trigger, right? And now this A is going to work as a clock pulse for our B. So it is going to remind, so here there is a negative edge trigger, here there is a negative edge trigger, similarly here and then here. So now when there is a negative edge trigger in this QA, QB is toggling from reset to set. And this QB is working as a clock for our C flip-flop. So here and all we are having the negative edge trigger. So it remains in the reset mode till there is a negative edge trigger. So it is happening only at the fourth clock pulse. Till then the C is in reset mode, and then it is maintaining the set mode. So if we write the clock pulse and the decimal counts for this particular mod 8 counters, then we can get all the counts from 0 to 1. Sorry, here it is 0, and then here again it is 0, 0, here 1, 1, then again it comes to 0, then here it remains 0 state for the 4 clock pulses, then it remains a high for the 4 clock pulses, then again it will go to the reset mode because there is a negative edge trigger at the B. So this is the corresponding truth table for the mod 8 flip-flop. So 0, 1, 2, 3, 4, 5, 6, 7. So it counted the 7 states. So the maximum count the mod 8 counter can count is 7. I hope you people have understood this concept. So these are all the references. Thank you.